Hello everyone, welcome to today's webinar. I'm Alexandra Taylor, an Assistant Editor at CNEN, and I will be moderating today's event. This webinar is titled Thermophysical Properties Characterization of Solid and Liquid Polymers Using the Flash Technique, and is being sponsored by the NETCH Group. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget in the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN online after the live webcast. The presentation is being sponsored by the NETCH Group. The NETCH Group markets itself as a mid-sized, family-owned German company engaging in the manufacture of machinery and instrumentation with worldwide production, sales, and service branches. The Analyzing and Testing business unit develops, produces, and markets instrumentation for testing the physical and chemical properties of materials such as metals, glasses, ceramics, and plastics using thermoanalytical methods. During the presentation, we will hear from Dr. Tobias Flock, who is a business manager in the polymer field with the NETCH Group. I will now hand over to Tobias.
Thanks, Alexandra, for this kind introduction. Thank you already for shortly introducing NETCH. I think we will hop right into business. So today I will present the webinar on thermophysical properties characterization of polymers using the flash technique, and I would like to show you how this technique can tell you more about thermal conductivity and transport properties of a wide range of polymers. As Alexandra pointed out, I will be available for question and answer afterwards as well. So just so you have some picture behind the voice that you hear already, well, that's me. I'm with NETCH Analyzing and Testing for 5 years, where I work as the business field manager for polymer applications. And my message is that laser flash is a smart and simple technique to analyze the transport properties of polymer materials. As I said, it works for many materials, metals, ceramics, and so on, but it works for polymers as well, and this is what I'm going to show you in this presentation. This is my agenda for today. So to get a basis for all of us, I would like to start with a short introduction of the flash technique. So just for you to get some basics. Of course, you can ask questions to that as well in the question and answers, but so we are on some common ground. Second point, I would like to show you how we at NETCH do this. I would like to shortly present you the LFA 467 Hyperflash. And the third point is why you're obviously all here. I want to show you some application examples where the flash technique can help you in analyzing your polymer materials and where it makes very well sense to use the flash technique with respect to other techniques. I will talk about thermal conductivity of a polymer melt. Second, I will talk on thermosetting resins and how we can analyze the heat transport even during the curing process inside the flash instrument. And the third point will deal with the influence of different filler materials. As many of you might know, because this is how we can adjust the thermal conductivity of polymer materials by using different fillers. And the flash technique is very widely used to characterize these materials. Well, let's start with some motivations, examples of heat transfer, and well, actually anywhere where you have a certain thermal profile in the parts you work in. Here is an example from electronics, well, you have some processor that is producing some heat, and you're trying to get rid of this heat by you're trying to get rid of this heat by applying different conductive materials. And as it's been used already, people use conductive polymers, for example, to build these kind of vents here that you see. So wherever thermal management, temperature management plays a role, it is of course important to measure the thermal transport properties. A second example would be in the automotive field. Of course, there's a lot of temperature produced in these kind of gasoline engines, so you would have to have a thermal management for any parts that you use of plastic material under the hood. And as well as heat transfer, this is one example, heat transfer in the seats is important because you don't want to be, let's say you don't want to be all sweaty, so you want to get this heat transported away. So, well, these companies have to take, in this case, BMW has to take care of this. And of course, heat transfer plays a major role in many other applications, such as brake pads, which are, sometimes they're made of ceramics, but mainly they're made out of some polymer resin material as well. So we would have to characterize this transport properties for the brake materials as well. And I have another very prominent example of thermally conductive polymers. And here I have two examples that I just picked from some data sheets from the internet. This is very detailed. I don't want to go through all of this. So this is on the left side, you see a polymer compound that is sold by Celanese. They call it cool poly. So this is a thermally conductive polypropylene. And on the other hand, we have supplier Enzinger that supplies a conductive, thermally conductive polyamide 6,6. And the interesting thing is, if you look closer to the data sheet, of course, they have to specify thermal conductivity because this is the property how these polymer compounds are adjusted. And if we take a close look and we look at these standards, they both mention different standards. In the case of Celanese, it's the ASTM E1461. And in the case of Enzinger, this is the DIN, this is a German standard, EN821. And both these methods refer exactly to the flash method to get the values for thermal conductivity and thermal diffusivity and specific heat. So that is, I think, a very prominent example where the flash technique is used. To take a step back still and to show you the world, let's say the entire world of thermal conductivity, of course, polymers are only a very small part of all the different materials. So we range in between thermal conductivities of up to 1,000 watt per meter Kelvin. This is the unit of thermal conductivity, where we have diamond down to insulation materials. Well, here down at the bottom at 0.01 watt per meter per Kelvin, you see gases or foam materials and so on, vacuum insulation at the very bottom. And you can see that polymers are used in a very wide range already. They can go up to the conductivity of pure metal as well, if we can adjust them by filler, which I will talk about later, for example. But also, of course, polymers are used for insulation materials, such as insulating polystyrene foams or so. So with polymers, we can span the whole range of thermal conductivity. So now, if I propose this kind of measure for my material, of course, I have to measure it as well. Well, the old saying in management is I can only manage what I measure, so we need something to measure. And there's different techniques. There's a laser flash technique, showed in red here, hot wire technique, quite an old technique, guarded heat flow meter, guarded hot plate, and also heat flow meters for more insulating materials. But this should not be what I will be talking about today. I will concentrate on the laser flash method that you can see here already that spans the largest range of thermal conductivities, and that is very fine as well to characterize the thermal conductivity of polymer materials. How does that work? Well, it's actually quite simple, or let's say in principle it's actually quite simple. If you look at the machine, it's still not so easy to build it, but the principle has been around from the 1960s, and we were one of the first, if not the first company to successfully commercialize this. What you see here on the right is a sketch of our sample. Well, we have our sample in the middle. This is this white disk here. And, well, we heat the sample to a certain temperature. Why do we do this? Because thermal conductivity is a function of the surrounding temperature. So my thermal conductivity will change when I change the temperature of the sample. So this is why we have a furnace as well in our thermal conductivity device. Second, we have a furnace around. We need a sample thermocouple to know the temperature at the sample. Then we need a power source. So for the flash technique, you shoot at the sample with a laser or a light flash. So physicists would say we use photons to shoot at the sample. And our sample will then absorb this signal and start to heat up. On the other hand, so at the top here, showed in green, you have a detector, and the detector will now watch the heat as it travels through our sample. And from this heat transport through our sample, we can deduce the thermal transport properties of our material. Generally, we use an infrared detector as this heat is transferred as infrared. And what is going to happen inside such a device is just shown in principle on the next few slides. Well, this is just a cut through the instrument that you see here on the left side of your screen, and we see this light shining onto the sample. On the right side, you see a sketch where we plot on the x-axis we plot the time, and on the y-axis we plot the signal or the temperature that the detector sees. So at first, of course, we shine the light on the sample and we don't see anything at the detector, so our signal is flat. What happens next is some of the heat now starts to travel through the sample, depending on the transport property of my sample, and our detector starts to see some signals. So our temperature at the detector, or the signal at the detector, is increasing. And this will continue until I reach a maximum of heat transport through the sample. And in the end, I will see the signal going down again to heat losses to the surroundings when my heat was traveling through the sample. So this curve is the curve that is characteristic for the kind of sample or for the kind of material that I scan in my laser flash apparatus. So what do we get from this? If we look at such a curve in principle, as it's shown here, this is actually the simplest model that you can get, and the red line just shows the temperature increase at the detector. On the x-axis again we see the time, and what we now do is we just look at the half time that the signal takes to travel through the sample, and this correlates. You see here in the middle it's written as the parameter A. This is nothing else but the thermal diffusivity. We call this number thermal diffusivity. And it's a direct measure for the ability of the material to transport the heat. I just see that my audio is very low every now and then, so I try to correct my microphone a little bit. I hope this is better. Maybe you could just give me short feedback. No audio, okay. Okay, I get audio is all good. Maybe so this is a reason of the connection. So maybe it's a good idea, I think, if you just dial in again, or you get out of the webinar and dial in again. Okay, I would just continue with my talk. So because we're quite not there, what we want to get is thermal conductivity. Thermal conductivity is always shown with the letter lambda. You see here at the bottom, this is the formula that we get. And for that, we measure thermal diffusivity alpha, we measure Cp, specific heat, and we need the density as well. So let's see what we need to calculate our thermal conductivity in the end, because this describes the ability to transport energy or heat. And that, of course, depends on the material that I'm using or what kind of filler I'm using, and that is the important number that I have to get to decide for whatever, for the thermal design of my parts. For that, we need the thermal diffusivity that we get from the LFA. This is the material transport coefficient. Then we need the specific heat capacity. That can be done, this is the ability of the material to store heat. This we can get from the LFA. We just look at the rise of the entire signal, and we can get this as well from DSC, differential scanning calorimetry. This is what we at NETCH use most of the time. And as a third number, we need the density in rho. This is specific mass of the material, and that can be obtained by just a density balance, or if you want to be more precise and you want to have the density as a function of temperature, for example, you could use a dilatometer to measure the thermal expansion and then correlate the mass and the expansion of the volume to the density as a function of temperature. So we have these three numbers, and now we can calculate the transport property, and that is the thermal conductivity lambda. There's well-known respective standards that refer to this technique. I showed you two of them already. The ASTM E1461 refers to the laser flash method, as well as DIN EN821. And one of the most prominent standards that we use a lot is the ISO 22007. Plastics Determination of Thermal Conductivity and Thermal Diffusivity Part 4 Laser Flash Method. So, well, if you run through this method, you will notice that, well, this is actually how we build our instrument, and this is what has to be done to obtain thermal conductivity and thermal diffusivity from such a measurement. So, well, that's it for the basics. So now I want to shortly sum up what are the main reasons, in my opinion, for the success of the flash technique. The first one you saw already, the method covers a very broad measurement range. So you can see a very broad measurement range in thermal diffusivity over 6 orders of magnitude. That's quite a bit. And that, of course, also results in a broad measurement range for the thermal conductivity. And this is why we can apply this to very different materials, such as low conductive polymer, as well as a very highly conductive metal material. The laser flash technique can easily be adapted to temperature-dependent tests. So here, we have devices at NETCH who can do tests up to 2,800 degrees. This is very special, and, well, that's not so interesting for today, because there's no polymer that I know that lives until 2,800 degrees. Nevertheless, sometimes it's also important to look at temperatures below room temperatures, and this is also where well, normally I would use liquid nitrogen to cool the device. So if I want to look at transport properties below room temperature, I could easily use the LFA as well, as we could also cool this furnace. So I could use a wide temperature range with the LFA. Third, sample preparation is easy. If I talk to customers, they just say, well, we have our samples that we prepare for mechanical testing, let's say like a dog bone shape or whatever. And from that, I could just easily cut a small piece. Normally, we recommend to use a thin disc of about 1 millimeter height. This is very perfect for polymer materials. So it's not that complicated. I don't need very big samples, but actually I can use just small samples that I use for other testing as well. So if I have a special mold for injection molding, I could easily derive my samples for the flash technique there as well. Third, it's a non-contact and non-destructive measurement technique. So I do not, and that plays a very important role in, if I look at conductivity, I do not have to care about contact resistance or anything, but the laser or the light flash is just the only thing that contacts my samples. Otherwise, I have a support to hold the sample, of course, but I will not interfere with the sample itself. And it's actually sometimes I see that people point out there's devices that have a very high energy, so they always point out we have the highest energy to shoot on our samples. That's actually what I do not want to have, but I just want to be, I just want to have just high enough signals so I get a response at my detector to be non-influencing on my material, and then I also get the best results for the LFA. It can be employed on multi-layer systems. I will talk about different models that we get just later on. It can also be employed to look at anisotropy. I will have an example on that. And I can have very fast testing times. Generally, for the light to travel through, even for polymers, even for low conductive polymers, well, that generally just takes a few seconds. And if I compare that to all the techniques that I know that are around, which use steady state methods, there's very good reasons sometimes, of course, to do steady state methods, but the LFA is just quicker. So I have this sample holder that can take up to 16 samples. So that's very easy to just scan them in a row. And let's say if you load this up, well, within a few hours, you're through with your entire measurement program that you want to have. So I think there's quite some reasons for the success of the flash technique, and well, the market has proven that this is true. So let's get back to our agenda, and I shortly want to show you how we do what kind of device that we have here at Netsch, and that is the LFA 467 Hyper Flash. Well, this is what it looks like. Well, it's just obviously a box. So all the flash apparatus and the detector is inside. So we take a look inside, and we have one picture where this is open. We can cover temperature range from -100 to 500 degrees, but I don't want to go too much into the features. We use a xenon lamp here at the bottom. And, well, this is what I've showed you at the beginning. This is where we have this light cone here depicted in a yellow that is traveling through our sample. The good news for you, well, this is all automated, so it's actually really easy to set up a sample. There's a graphical interface, and you just point on the sample that you want to measure. You set the sample, and off you go with the measurement. So there's a very, very, very nice surrounding measurement software that comes with it as well. We have zoom optics that just gives you better results, and data acquisition is very fast. As I told you, this just takes only seconds, and we have a time resolution that is even higher in the millisecond range. Let's take a short look on the different models, and that's something that you will get into contact with if you look at the laser flash technique. There's many, many different models available in the literature, depending on the boundary conditions that you have for the kind of sample or the transport that you have inside your sample. So Well, I can say we have the widest range of models packed into our software. The good news is, even here, you don't have to be a professional to know all these guys. Here, there's all different names: Parker, Cohen, Azumi, Clark Taylor, and so on. Improved Cape Lehman model, whatever, because this is all simplified in our software. So you can easily find, so you can actually just click through the models and find which model is most appropriate for your sample, to take into account heat loss, to take into account radiation that happens inside your sample that does not contribute to the normal heat transport. For example, if you have transparent samples. And at the bottom here, you see all standard modes allow for a combination of heat loss, pulse correction in various baseline types. So we have to take care of the pulse shape, because if we shine, well, the signal that we get in the end just depends on the kind of pulse that we shine on the sample, and we have a pattern on this. Finite pulse correction, and we also have baseline correction to just get the best signal. There's a lot more, and I can tell you there's probably specialists here that could talk only for an hour about these different models. You can be very sophisticated, but just 2-3 more things. I told you there's multiple layer models. If you have, let's say, a coating that is placed on a just a metal sheet or something, that can be taken into account here. And we will see some other examples. We can measure in plane. So if you have heat transport along your sample in plane, that is very interesting for anisotropic materials. And we have a very new model that is taking penetration of my light pulse into account. The take-home message for you of all these models is, the better the model fits to your data, the better your results. So it makes very much sense to, from all these models, to select the best kind of model to get the best results on your laser flash measurement. And as these models are very sophisticated, I can say that we can take care of all the different surroundings to provide the best data of the thermal diffusivity and to get the most accurate data of the thermal conductivity later. Well, now let's shortly talk about different sample holders. You see here there is a wide variety of sample holders available for different sample sizes, for square samples, for round samples, for big, small, whatever you want. There are special sample holders for liquids and pastes. I will need them later. There's special sample holders for powders, special holders for in-plane samples as well. So there's not many samples that we cannot probably measure. But let's go on with the different application examples that I have for you. At first, I want to start with a thermoplastic material. And here we look at polycarbonate. It's actually, polycarbonate is mainly transparent or translucent material. So we coat this with graphite in order for the sample to absorb the flash pulse and to measure the thermal transport. Well, what you see here is actually a typical plot as we plot the parameters that we get from the LFA. On the left axis in red, you can see the thermal diffusivity. This is the sole property that comes from the laser flash. On the right hand, you see in green, in light green, specific heat capacity. This can come from either the laser flash method or from differential scanning calorimetry. And together with the density of the material, we can calculate the thermal conductivity. So this gives you the full sketch of the thermophysical or thermal transport properties of your material, and we end up with this blue signal here as thermal conductivity. The interesting thing here is that we measured this polycarbonate past the glass transition. So we just go over the glass transition. So this actually gets quite soft, and we get into the rubbery state of the material. Nevertheless, as we still have this in our sample container, we can just go past the glass transition and still measure the transport properties just within one sample. Next sample shows you a semicrystalline sample, and this is polypropylene. And again, you see depicted thermal diffusivity in red, specific heat capacity in green, and thermal conductivity in blue. And we can see two things because we can see the melting. Melting shows up as the step in the specific heat capacity and as this, let's say, peak form in the thermal diffusivity. So in the end, well, that's quite an interesting property to look at thermal conductivity of polypropylene, because if you do, let's say, if you're injection molder and you use mold flow for your for the simulations, well, it's obviously quite important. If you look at the thermal conductivity of your material and at how the material behaves inside your mold as you inject the polymer, because the thermal conductivity from room temperature changes from 0.14 watt per meter per Kelvin to 0.22 watt per meter per Kelvin in the melting material. So if you don't take this into account, well, you're just wrong by about 20%. If you're not taking the exact transport property into account. And if you want to take this value for simulations, such as mold flow, for example, this does play an important role. Next example we look at is thermosetting resin. We look at, there's many kind of resins. Most prominent example would be epoxy resins, but polyester resins and so on. They also come in the liquid state normally. And they're commonly used as adhesives, encapsulation materials for electronics, or fiber reinforced composites. So two things, encapsulation materials in electronics. Well, that's a very prominent example where you want to adjust your thermal conductivity, because that's a typical example where you have some kind of integrated circuit that is just sitting underneath your encapsulation, and you want to get rid of the heat. So you have to adjust the thermal conductivity of your encapsulation material. And this is obviously what is being done. So you can buy these epoxy resins in with different kinds of conductivities. This is true as well for fiber reinforced composites. While that's a whole different material, heat transport gets anisotropic. You have fibers as well. So this is actually quite a complex material. But if you have this inside some let's say some heating profile, of course you would have to know the transport properties of this material. And that is very different in the plane as your fibers go, and if the heat just travels perpendicular to the fiber layup of your material. So this would be a prominent example where anisotropic heat transport plays an important role. How can we measure epoxy resin? Well, there's a special kind of sample holder, and we place the liquid between two steel plates. You just see the setup here to the right. And we actually put our sample inside the sample ring that is covered by an upper and lower sealing disc and placed inside this metal frame. And this is a nice example where we have to use a 3-layer model where heat travels through these two metal sealing discs. And we still can take this into account by the different models. And in the end, we want to derive the property of our epoxy resin in the middle. And well, you could just discard the sample setup, the upper and lower sealing disc and the sample ring, because well, this is actually glued nicely together after the experiment. And I'll show you what happens during the curing reaction as we heat up the sample now. Well, again, we see two properties here, and we measure the thermosetting resin as a function of curing time, in this case, and curing temperature. So I will take you through this graph. In red, again, we depict the thermal diffusivity, and in blue, we depict the calculated thermal conductivity. And you see thermal diffusivity increases with time. And if you take a closer look, we measured this whole procedure at 3 different temperatures. So if we turn up the temperature, we measure at 60, 80, and 100 degrees. And if we turn up the temperature, well, we cure our sample, and we cure it faster and faster. So if we look at the 60 degrees, well, it takes quite a while as we wait for the sample to cure and our heat transport increases. If we take the 100-degree measurement, we see that our curing takes place much faster, and we get a higher thermal conductivity after our sample is cured. So this is nothing else but a curing reaction watched with respect to the thermal transport. So the interesting thing is that thermal diffusivity and conductivity can be measured even during the curing of an epoxy resin. And last but not least, I would like to talk about the influence of different fillers, as I mentioned at the beginning, because this is how we can adjust the thermal conductivity of a polymer, and there's commonly different kinds of fillers applied to do so. Well, this is just an overview. Well, there's many different filler materials, very commonly used. Well, if you look at these brake pads, this is quite an interesting example because there's actually quite some different materials that people put into this material, even pieces of metal in order to adjust the thermal conductivity. Of course, also different properties. You could also use chalk to adjust, or chalk has an impact on the thermal conductivity. Carbon black as well, silica materials, and to carefully adjust it, we will see an example of boron nitride, where boron nitride is used, and a second example where we will use carbon nanotubes to adjust the thermal conductivity. First of all, if you want to do some research on the fillers itself, you could do this by using our pressure sample holder. So again, to the left, you see the principle here. We have 2 support planes. You put the sample powder in between the upper support plate, and then you have to set a certain pressure that determines the packing of your filler material. And well, that just depends on what you want to look at. And then we take this kind of sample arrangement and just shine through our through the sample holder itself. We apply multi-layer model to derive the transport property of our sample, and we get the following result. What we did here is we looked at 3 different filler materials. So number 1 in blue, number 2 in red, and number 3. So this is just the 3 different materials. And it's shown in this black dashed arrow already. We have a decreasing particle size between these different materials. And what we now do is we increase the density. Well, how do we do this? We increase the density as we pack the sample more and more. That just increases the density of the powder. And on the left axis, you see the thermal diffusivity A. And as we increase the density of the material, our thermal diffusivity also increases. And it increases most significantly for the larger samples, so for the red sample that you see here. Well, that was just an example of pure filler, but now we want to look at polymer materials that are used with some filler material. Oh, sorry, I was too fast. Let's go 1 slide back. And this is an example where boron nitride filler was used to adjust the thermal conductivity of a plastic material. Again, you see thermal diffusivity on the left, thermal conductivity and specific heat on the right, and the x-axis shows different contents of boron nitride in our samples. And as we see, that's quite interesting. There's actually nothing happening until we reach a filler content of about 50%. Why is that the case? Because this is when percolation is starting and when the boron nitride particles are starting to see each other. Because after that, if we increase to 80% of boron nitride, we get a very strong increase in the thermal conductivity. So we also learn if we want to really alter the thermal conductivity of a polymer material, we have to use quite a bit of filler material to adjust the thermal conductivity. And boron nitride is very commonly used. What is also used, especially in research, is carbon nanotubes. In this case, we have a sample with peak polyether ketone. And first sample has no filler, so thermal diffusivity, thermal conductivity, and specific heat. And we measure this actually over the glass transition here. Glass transition is at about 170 degrees, so you can again see this kink in our specific heat capacity and in the thermal diffusivity. But that's not the point, because now we add 7% of carbon nanotubes. And well, we just see, I just tell you that from the values, thermal conductivity increases with 7% carbon nanotubes. We get quite an efficient increase by 20%. The point about carbon nanotubes is that they are anisotropic. They're actually really anisotropic. This is basically why they're used and why they're so interesting here. So we want to know the transport properties in different directions, and we want to look at anisotropy. For this, we take a special sample holder to do in-plane measurement. We call that laminate sample holder. We cut our sample as it is described here from E, F, G to H. We just cut our sample and we just stack it into our sample holder plate. And well, we fix it and place it in the LFA apparatus. And with that, we can measure the anisotropy of our thermal conductivity. And we expect quite a significant effect. As you can see here, the dashed lines on the top are depicting the in-plane transport properties for a peak filled with 14% of carbon nanotubes. And hey, we see this is quite anisotropic, and obviously we have more heat transport in plane than we have perpendicular to the plane, and that can easily be seen with the LFA technique. And this is actually one of the specialties of the laser flash technique, because laser flash is the only technique that can measure the anisotropy in thermal transport. And this actually plays a major role if you want to put different filler materials. Boron nitride is another example for an anisotropic materials. So you have to check the anisotropy of your heat transport if you want to adjust, if you want to use fillers to adjust the thermal conductivity. The thermal conductivity of a polymer sample. And last slide of our samples. Well, we just see that we get approximately a linear increase in the thermal conductivity as we add more and more carbon nanotubes to our sample. We get higher conductivity for higher temperatures. Thermal conductivity is higher at 200 degrees than it is at 25 degrees. And with more, as we increase the carbon nanotube content from left to right, we also get increased thermal transport. So with that, I'm about through with my agenda. I hope you learned some things today. I started with the basics of thermal conductivity using the flash technique. I showed you how we do things at Natch here, how the LFA 467 HyperFlash works, and all the different options that we have, all the different software models. Well, there's a lot to it, but don't worry, there's a lot of other materials that you can get on the homepage if you're interested in that. And well, you could also just contact our specialists on that. And we looked at 3 application examples. I showed you that you can measure thermal conductivity through a melting transitions with one and the same sample holder inside your laser flash device. We looked at thermosetting resin, so you can even look at liquid-solid transition for thermosetting resin inside this LFA device. And we looked at the influence of different filler materials, especially at the anisotropy of thermal conductivity that you would have to look after if you have an anisotropic filler. Okay, to sum up at the end, I hope I could show you that the LFA method allows for fast and reliable measurements of the thermal diffusivity and conductivity of solid and liquid polymers over a broad temperature range. Due to the speed of the method and the high accuracy, more and more researchers replace existing stationary methods with a flash technique, so it just takes you a few seconds to do the shot and, well, let's say a few more minutes to do the entire experiment. And we could do even critical sample geometries such as liquid polymers, I showed you that, or even liquid metals we could do as multi-layer samples, as well as anisotropic samples can be analyzed using the LFA method. And with that, I'm through for my part of the talk. If you want to find out more, just contact us via www.natch.com/LFA467. Yeah, my name is Tobias Flock, and I thank you very much for your attention. And I think the talk is open for some question. And I would go back to
thank
Alexandra.
you, Tobias, and we'll move on to the Q&A section now. So the first question is, which is a minimum area that can be characterized, and can it be applied down to the micrometer scale?
The minimum area of the sample. So, well, actually, you have to get some response on your detector. So, actually, the sensitivity of the detector limits the area that you need to shine some light on. So, the smallest sample goes down into the millimeter range. However, that might not be appropriate for polymer samples. So if you have smaller samples, maybe we should discuss in detail what kind of application you have to see why you're looking only at the micrometer range. So it's a little bit tough to answer. I would take a closer look on that.
What about the precision of the technique at ambient and high temperatures?
Precision, I would say, precision is, we say, about 3% at room temperature. I can also say precision is decreasing as the heat profile of the sample changes. However, with respect to steady-state technique, I think I can say the precision is higher as we do have just a very confined sample. And with that, we also have very defined boundary conditions. And all these different models that I showed you, they take very good care of all these boundary conditions. So just to give you a number, I think 3% precision is what we generally give. This can be better for your kind of sample, but it should not be, let's say, much worse. But that is what the technique can do.
Do powder materials work well with measurements, or do we have to compress them to discs?
As you saw, well, the thermoconductivity of powder materials very much depend on the packing of the powder. So it does make a lot of sense to compress them. But that is just a parameter that can be adjusted with maybe I can go back with the slides here. I try to be fast. Or no, I can. Yeah, it works like that. Well, that's the powder sample holder that you see here. So you have to adjust the pressure in order to get reproducible results on powder samples. So you can as well just use discs that you compressed before with a certain pressure. But so yes, you would have to set the pressure in order to measure powder samples.
How sensitive is the measurement regarding the detection of delamination in a multi-layer stack?
Delamination is actually quite easy to detect because materials generally conduct heat quite much better than air. Air is actually insulating for the heat transport. So whenever you have delamination, you will just see that the thermal conductivity decreases. And that is so let's say you heat up your sample and you get delamination, and there's jumps in your signal. I would then delamination could be a very good reason for this to happen in your signal.
Are there any challenges in measuring amorphous materials?
Amorphous materials, as you just saw, we measured the polycarbonate sample. That's an amorphous polymer, but we can still go across the glass transition. You have to take care of the softening of the material, of course, but this could be done in a, let's say, kind of looks like this 3-layer sample holder that you can see here that we use for the pressure sample holder. An arrangement like that could also be used for amorphous samples, so you just don't lose the sample when the sample is softening above glass transition temperature. But in general, well, amorphicity just alters, well, you get a different transport properties than for crystalline samples, but that's actually what you want to measure. So there's no special care that you have to take if you want to measure amorphous samples.
Are there specific holders for liquid samples or the laminated ones available for LFA 427?
You mentioned 427. 427 is another product from our portfolio that's generally used for even higher temperatures. So, but its principle is just the same. It's a laser flash method. There are special liquid sample holders available for the 427. I don't have them here right now, but I can again go back to an example for the liquid sample holder for the 467 that I showed here for liquid resins. And well, that's just a big picture of all the different sample holders. With respect to 427, I think we would just come back to you after the talk if you're interested in liquid sample holders there. But yes, they're available.
Is the sample volume critical in this measurement, and does it normalize the sample dimension when comparing a film sample to a powder sample made of the same material?
You would have to take the sample dimensions into account because so the thickness of your sample enters the calculation of your thermal diffusivity. So we have to normalize our thermal diffusivity with respect to the thickness. So I doubt that you would get the same value for a powder sample and for a film sample with respect to the height, but I don't have any results in my mind right now, but this is something that I would maybe ask our specialists in the lab here if we have comparisons like that. But yeah, I would just say that maybe you just come back on that and we check that.
When using the graphite coating, how much will it affect the measurement?
The graphite coating generally, so if we use, well, we talk about polymers here, if we apply the graphite coating, you saw the thermal conductivity of diamond. Well, that's not quite graphite, but the thermal conductivity is negligible with respect to conductivity of the polymer materials in a very wide range. And well, we just need the graphite coating in order for the sample to absorb our radiation from the flash source. So I would say it does not play a role, but there's just no other way to measure translucent samples. So let's say for the example I showed you, that was here we go. That was the polycarbonate. You don't see the effect of the graphite in this picture here.
If a polymer moves during these tests, will you get the same result?
Actually, it should not. It depends on what moves. If you just give the device a neat push, well, as it changes the boundary conditions, it will also change the response that you get on your detector. But it just depends on much your sample actually moved. But normally, I would say if you have a disc-shaped sample, the sample should not move as much as that it alters your measurement. But well, it depends. It depends on how much your sample moves. I don't know if you have any live polymer, but generally this is not a problem for the flash technique.
What is the minimum thickness of a film that you can measure?
Minimum thickness of a film. So you can get down to the micron range, but clearly said there's different techniques to measure. There's different methods to measure thermal transport. There's different techniques to measure thermal transport properties of films, such as thermal reflectance. So if you're interested in these kind of techniques, such as thermal reflectance, I would just ask you to contact us via the website. This is not mainly LFA, or to contact your sales representative. So we give you some more information on that. But generally, micron range can work, but there's can also be better techniques to look at that.
Can this technique replace DSC?
Oh, it depends on what you want to do. You can look at specific heat capacity also with this device, and sometimes the specific heat, the precision of the specific, or the accuracy of the specific heat capacity you get with the LFA is indeed sufficient to get a reasonable specific heat capacity of your sample. However, DSC, differential scanning calorimetry, I guess it's a story on its own. So it can do much more. So I would say it actually will never replace different scanning calorimetry. But with respect to thermal conductivity, sometimes it's sufficient. So, Alexandra, question, is there any more questions from the audience that I can answer right now? I think we approached just about the full hour.
Yeah, I think that's about all the time we have. But thank you again, Tobias, for your fascinating presentation, and thank you to our participants for being a great audience. Be sure to check CNEN or CNEN online for information on the next edition of CNEN webinars. Thank you to On24 for technology and production services, and thank you to the Netsch Group for your sponsorship that made this interactive webcast possible. For CNEN webinars, I'm Alexandra Taylor. Goodbye.